My name is Tim Hudson, and in collaboration with the Intelligent Transport Systems Group at the Australian Centre for Field Robotics, my thesis topic is classifying pedestrian interactions with autonomous vehicles. As autonomous vehicles transition toward mainstream use, a major obstacle is the complex behaviour that pedestrians are capable of. Whilst autonomous vehicles are able to use their various sensors to avoid running into pedestrians, they are not able to understand their behaviour. This is evident in contexts such as pedestrian crossings, where negotiation between a human driver and pedestrian is often performed using subtle and implicit cues. With no human driver, cues such as eye contact and body language are unable to be interpreted. A lack of contextual information, such as whether a person has noticed the vehicle or if they are distracted by their phone, may lead to inefficient and potentially unsafe interactions. As a result, this problem led us to develop the following research question: how can an autonomous vehicle understand pedestrian interactions? Therefore, the aim of my project is to develop a system that is able to detect, track, and classify pedestrian interactions to inform the decision-making process of an autonomous vehicle. By quantifying pedestrian behaviours, this will allow autonomous vehicles to interpret contextual information and potentially improve the efficiency of interactions. For my solution, I've developed a system that encompasses multiple open-source software modules that process camera data to estimate the body pose, head orientation, and gaze direction of a pedestrian. The entire system uses ROS as a middleware, which facilitates the transfer of data between modules. Using examples, I'll break down the high-level system architecture and explain the purpose of each software module. Firstly, the playback tool extracts an image frame from video or camera data and publishes it to each module. For this project, I use video footage from the USYD campus dataset, which is a compilation of driving data from a vehicle performing the same route around Sydney Uni campus. You Only Look Once, or YOLO, is a state-of-the-art object detector which is capable of classifying 80 different objects. YOLO takes an image file and produces bounding boxes around pedestrians over a certain confidence level. DeepSORT uses deep learning for the tracking of custom objects. The pedestrian bounding boxes are passed to DeepSORT, which then tracks them over time with an associated ID. OpenPose is a 2D body pose estimator, which is able to predict the location of body pose key points in real time. Using image data, it will estimate up to 25 key points for each pedestrian. OpenHeadPose then uses this body pose data to estimate the roll, pitch, and yaw angles of a pedestrian's head, represented by X, Y, and Z vectors. In this way, head orientation and gaze direction can be estimated. All of this data is published to the pedestrian tracker and synchronized for processing. Body poses and bounding boxes are paired to represent individual pedestrians, and noisy data is filtered out. Once processing is complete, it will publish all pedestrian data and send a completion flag back to the playback module to request the next frame. The output data can be overlaid onto the input video, or it can be displayed separately. By tracking the body pose, head orientation, and gaze direction of pedestrians over time, this information can be used to classify their behaviour. For this project, I've implemented a simple classification system represented by the bounding box colour of pedestrians. Red indicates a pedestrian that has not seen the vehicle. Green indicates a pedestrian currently looking at the vehicle. Blue indicates a pedestrian that has seen the vehicle but is not currently looking. And orange indicates a pedestrian that is distracted by their phone. As shown, the output video displays great success in tracking pedestrians over time, especially for people that are closer to the vehicle. Whilst the classification system is very simple, it shows promising results for generating contextual information to contribute to the decision-making process of an autonomous vehicle. A challenge with using camera data alone is that dimensional data, such as depth or distance, cannot be determined, as pixels do not correlate to real-world measurements. Furthermore, pose estimation becomes significantly less accurate the further away a person is, and sometimes struggles to differentiate pedestrians that are standing close together. Therefore, the accuracy of this system is heavily dependent on both the image resolution and distance of the target. Another issue is the significant amount of processing power that the system requires, running at about 2.5 frames per second. Although the final system does not operate in real time, it may prove incredibly useful for offline analysis of footage and automatic annotation of datasets. Through this project, I've learned a lot about software development and deep learning techniques. Most importantly, I've learned that predicting pedestrian behaviour is an incredibly complex problem. In terms of future work for this project, optimizing the system to perform in real time would be incredibly valuable and would allow operation on autonomous vehicles in the field. Furthermore, implementing a deeper classification of interactions would enhance the contextual information that is generated. A final recommendation would be to incorporate data from additional sensors such as LiDAR to add dimensionality to the results. Ultimately, it's important to ensure that autonomous vehicles are able to interpret as much useful information as possible so that they can act in a safe and efficient manner.